part 2. Hopefully you've already taken a look at the first half of these for the Unit 4 review questions. I'm going to go over the last 21 questions for this Unit 4 review. All right, so let's start with number 22. Number 22 gives us the graph of the derivative of our function f between -6 and +8. It says of the following, which best describes the graph of the function f on the same interval. So if you look at all the answer choices, you've got some possibilities for relative minimums, relative maximums, and then points of inflection. I'm going to start with the minimum and the maximum here. Essentially, when I look at the graph of the derivative, similar to what we talked about in many problems in the first part, the graph of the derivative, the sign of that is going to tell you where your original function is increasing and decreasing. So if you notice at the beginning of this, our f prime function is positive from -6 until -2. That's when it crosses the x-axis. So we're actually increasing. Our original function is increasing until you get to -2. All right, the moment it switches down to the negatives, we are now decreasing. So if you think about, and we do this in class, my mind, I'm showing my hand, but if I'm increasing to decreasing, that's going to be a relative maximum. So that means we have a relative maximum at that -2 value. All right, with the same idea, right, the function is decreasing from -2 all the way until it looks like about 7. All right, maybe even 6. So I'm sorry, not 7, not 6, into 7, yes. So if you look where we cross the x-axis at x equals 7, now we're back into the positive y values for our derivative. So that means we are going from our function is decreasing to increasing. So we have one relative minimum. All right, so to me, that's going to rule out all the answer choices C, D, and E. So just understanding what we've talked about in the past about the sign of our first derivative, all right, that's going to help us narrow it down to A or B. So let's talk about points of inflection, okay? So points of inflection, the way that I look at this one is when you're changing, all right, from concave up to concave down, all right? So another way to think of it is you're looking at the second derivative, all right, where the second derivative would be 0, okay? So the way I look at this is wherever the second derivative would be 0. So it looks like we have one here, we have one here, and it looks like we have one there. So that's 3 spots where the derivative of the first derivative is actually 0. So that's 3 points of inflection, all right, for number 22. So that's going to tell me that number 22 is A. Let's go to 23. All right, now 23 gives us a function, and it wants us to find a relative maximum. All right, so the way to do this is to find the critical points. So I'm going to find the derivative. So d dx of 3x to the 5th power minus 4x cubed minus 3x. That's going to be 15x squared. Oh, not squared, sorry about that. 15x to the 4th power minus 12x squared minus 3. And I want to set this equal to 0. I could also find a critical point, whatever makes it undefined, but this is a quartic trinomial, so we're not going to have to worry about any undefined values. So let's set it equal to 0. And now I'm going to take out a 3, and it leaves us with 5x to the 4th power minus 4x squared minus 1. As I've mentioned many times, because that 3 doesn't have a variable with it, I don't really care about it. So now I'm going to try to factor, again, using, you could use your factors of a times c to add to b, but I'm going to just use 1 and 5 for the beginning of my x squared terms. I know factors of 1 are just 1 and 1, so I just got to get the signs right here, and I need my 5x squared to be negative, because I need it to be negative 5x squared plus 1x squared is negative 4x squared. So if I set each of these equal to 0, the one on the right is pretty straightforward, right? That's the difference of 2 squares. So x equals plus or minus 1. Now the one on the left, right, if you notice, once I move this 1 over, it becomes a negative. And you guys learned many years ago that if you square something, it's always positive. and a positive times a positive, right? That positive 5 will never give us a negative. So these solutions would be two, where'd you go? There we go. So two complex solutions, which we only care about real numbers, not imaginary. So really, it's just these two that I care about. So watch what I do with that. That means I'm going to set up, like we've done in the past, negative infinity to negative 1, negative 1 to 1, and 1 to infinity. And I'm going to do my signage. All right. So I'm going to do my sine of my derivative, sine of f prime of x, given my conclusion. So if I plug in, again, I'm just plugging into the derivative here, so I'll highlight which one I'm doing. All right. If I plug in a negative 2, all right, that's going to give me negative 2 squared, which is 4. That's a positive. Negative 2 squared is 4. That's also a positive, so this will be a positive. Let's plug in 0. All right, 0 is going to give me a positive times a negative, which is a negative. Plugging in 2 is going to give me a positive again. So that means my f of x function for my conclusion is increasing, decreasing, and increasing. This asks where is it a relative maximum. So relative maximum would be increasing to decreasing, increasing to decreasing. So it's actually going to be in between these first two intervals. So at negative 1 is where I'm going to have my value that is a relative maximum from increasing to decreasing. So that's going to be A. All right, let's go to 24. Same process here, guys. All right, I'm going to find the derivative of f prime of x. Now, it's going to be a little tricky here because I have x to the 2/3 power. So 9 times 2/3 is 6. Come on. There we go. And then if I do 2/3 minus 3, 3/3 or 2/3 minus 1, I get negative 1/3 and then plus 3. All right, so I'm going to rewrite that as 6 over the cube root of x plus 3 equals 0. So my critical points would be whatever makes this undefined or would be set equal to 0. Now, what I noticed is that I actually do have an undefined value here. X equals 0 would work, right? Because the cube root of 0 is 0. 6 over 0 is undefined. So one of my critical points is going to be at x equals 0. All right, now let's set it equal to 0 here. So I have negative 3 equals 6 over the cube root of x. I'm going to make a proportion. So that gives me negative 3 times cube root of x equals 6. Divide that over. I get the cube root of x equals 6 divided by negative 3, which is negative 2. Cube both sides, and you get negative 8. All right, so those are my critical points. 0. Oh, where'd you go? There we go. My critical points are 0 and negative 8. So I'm going to go ahead and do my same thing I did before. Negative infinity to negative 8. Negative 8 to 0. And 0 to infinity. I need to find my signage to make my conclusion. So if I plug in negative 9, remember I'm plugging into the derivative here. So plugging in here. All right, and if you want to use a calculator, you can. I'll go ahead and show you using Desmos to do this. So I'm going to do 6 times negative 9 to the negative 1/3 power plus 3. So 6 times negative 9 to the 1/3 power. Negative 1/3 power? Negative 1/3. Real quick. Yes. Plus 3, so that gives me a positive. So that's positive. Oops, change it back. There we go. So a positive. Plugging in negative 1. So doing the same thing, but making this a negative 1 gives me a negative. And plugging in positive 1 gives me a positive. All right, so that means that we have our f of x function. So this is our conclusion about f of x is increasing, decreasing, increasing. We're looking for a relative minimum. So relative minimum would be decreasing to increasing. So decreasing to increasing. So that's happening at x equals 0, which is E. All right, let's go to 25. We have a derivative, and it says that how many points will the graph of f have a relative maximum? So they already found the derivative for us. That's nice. This is not going to be undefined anywhere, so I just need to set it equal to 0. So I have x equals 0, positive 2, and negative 3. So I'm going to set up my different intervals like we've done many times now. All right, do my sign analysis for this first derivative so I can make my conclusions. If I plug in negative 4 to the fourth power is a positive. Negative 4 minus 2 is a negative, so that's still a negative right now. Negative 4 plus 3 is a negative times a negative is a positive. Plugging in negative 1, I get positive times a negative, which is a negative, and negative times a positive is a negative. Okay, and then we have plugging in positive 1, I get 1 to the fourth power, which is positive, times a negative, times a positive, which is a negative again. All right, and then finally plugging in 3, I think everything's going to be positive. Excellent. So increasing, decreasing, decreasing, increasing. So it says, how many points will the graph of f have a relative maximum? Remember, relative maximum is increasing to decreasing. So that's only happening one time at negative 3, where it's increasing to decreasing. So 25 is B. Let's do 26. All right, so we have f is a differentiable function, the domain 0 to 5. If we know that f prime of x, the derivative, is negative on the intervals, so let me do my intervals again here. So 0 to 1 is negative, 2 to 3 is negative, 1 to 2 is positive, and 3 to 5 is positive. So that means my conclusion would be that the original function is decreasing, increasing, decreasing, and then increasing. Okay, so that means we're looking at how many relative minimum and maximum. So I'm starting out decreasing to increasing. So I have a relative, minimum. So decreasing to increasing at 1. Then I'm increasing to decreasing. So that's a relative maximum at x equals 2. And then finally, I'm decreasing to increasing again. So another relative minimum at x equals 3. So that tells me I have 2 relative minimums and 1 relative maximum. 2 relative minimums and 1 relative maximum. Looks like that is C. Let's go to 27. Now, this is from the same lesson before. I can show that for you. Again, this is a lesson that you had to do on your own. I think it's 4.5. Let me just confirm. No, 4.6. 4.6? I lied. There it is. So 4.4, right? What we just did was looking at, is it 4.3? Wow, you're right. It's 4.3. All the way to 4.3. My bad. I'm sorry. Anyway, we've been doing lots of critical points here. This last part of 4.3 is looking at over an interval. So we did some absolute extrema questions over an interval. So we did these at the second part of 4.3. Okay, you'll find that there. Okay. So let's go, where were we? Picking up with 20, almost there. So close, guys. Too far. 27, here we go. So first thing you do when you're trying to find the maximum, the absolute maximum or minimum on an interval that they give you is you want to plug in your endpoints. I'm going to do f of 0 and f of 6, all right? The 0 one's pretty straightforward. 0 minus 0 is 0. 6 might be a little bit more challenging, so you can go to Desmos and plug it in, or just use your cell phone with you if you have it. So I'm going to do 6 cubed minus 6 times 6 squared minus 15 times 6. So we have 6 cubed minus 6 times 6 squared minus 15 times 6. I think that's what it is. I'm going to confirm. Okay, so that's negative 90. Okay, so now I need to find the critical points. And if those happen to be in my interval of 0 to 6, then I'm going to plug those back into the original function. So find the derivative. I'm going to skip a step here of like showing you that I'm finding the derivative. I'm just going to find it. 3x squared minus 12x minus 15. That's a quadratic trinomial. I don't have to worry about anything being undefined. So I just need to set it equal to 0 so I can factor it. So I'm going to factor out a 3. X squared minus 4x minus 5. Again, like I said a few problems ago, that 3 doesn't have a variable with it, so I don't care about it. So it becomes x minus 5 times x plus 1. Okay, so my two critical points are positive 5 and negative 1. But if you notice, in the interval of 0 to 6, negative 1 is not in the interval. So all I care about is this 5. Okay, so I'm going to be plugging in 5. So do f of 5. I'm going to see if that's going to end up being my absolute maximum. Or it might be one of my endpoints. So I'm going to plug in 5. You can just replace the 6 or duplicate it like this, your choice. So plugging in 5. And you get negative 100. All right, now, if this problem was asking for the absolute minimum, then it would be when x is equal to 5. But it says the absolute maximum, so that means it's actually going to be the highest y value, which is 0. All right, so 0, 0 is my absolute maximum for 27. So letter A. Let's go to 28. All right, same process. We're going to do the same thing. I'm going to plug in my endpoints. Okay, then I'm going to find the derivative to find the critical points and see if any of those are on my interval. So let's plug in these two endpoints to this function using Desmos. So 4x cubed plus 3x squared minus 6x plus 1. So delete these. So 4 times, is it negative 2? Yes. Negative 2 cubed plus 3 negative 2 squared minus 6 times negative 2. Here we go. So that value is negative 7. We'll do the same thing for positive 1. I'm going to copy it. Change all these to positive 1. That gives me positive 2. Okay, so now I'm going to find the derivative of this g of x function. So g prime of x is 12x squared plus 6x minus 6. Again, it's a quadratic trinomial. Don't need to worry about anything being undefined, but I'm going to factor it to get 2x squared plus x minus 1. The 6 you can just ignore. So I know this is 1 and 1, and I need the 2x to be positive. All right, so we have x equals 1/2 or negative 1. If you look at the interval, positive 1/2 and negative 1 are both in this interval. So I need to evaluate g of 0.5 and g of negative 1. Once I have all 4 of those, I guess 2 more would give me all 4, I can evaluate and see which one has the highest, the lowest, the minimum, the lowest y value. So I need 0.5 and negative 1. So I'm going to duplicate again and plug in 0.5. It gives me negative 0.75. I'm going to duplicate one more time and do negative 1. All right, so I have negative 0.75 and positive 6. All right, so I'm looking for the absolute minimum. So I'm going to highlight the y value that is the smallest, and the y value of the smallest is negative 7. So the answer is going to be A. All right, let's go to 29. Okay, so this says we have the graph of the second derivative is shown. What are intervals on which the graph of the function is concave down? Now, as I mentioned earlier, the sign of the first derivative will tell you if the original function is increasing or decreasing. And the sign of the second derivative will tell you if the original function is concave up or concave down. That idea is concave up, kind of like a cup can hold water. And concave down is like a frown, and water would just kind of roll off the side. Okay, so when I look at this, if it says on which intervals would the function f be concave down, I'm looking for where is the second derivative negative. Okay, and the second derivative looks like here is negative at -2 to -1, -2 to -1, and 1 to 3. So when I look at my answer choices, that's E for 29. Let's go to 30. This one says, when we're looking at the function, we have the second derivative, then the graph of the original function is concave up. I'm going to do the sign analysis for the second derivative to determine where my function is concave up or down. So I just need to find critical points for this. Can't make it undefined, but we can set it equal to 0 for the second derivative. One of the critical points is 0, and the other is -2. Okay, so I'm going to do my analysis for my intervals here, negative infinity to -2, -2 to 0, and 0 to infinity. Do my sign of, this time, the second derivative. So I'm going to plug in -3. -3 by itself out front is a negative. -3 plus 2 is a -1 squared is a positive. That's going to be negative. So my conclusion is concave down. If I plug in -1, same thing happens. A -1 outside, and then -1 plus 2 that's going to be squared. So a positive times a negative is a negative, so still concave down. And finally, if I plug in +1, everything's positive. So we have our answer for where is it concave up. It's concave up on this interval between 0 and infinity, which is values for x that are greater than 0. Okay, 31. Now, this one is a really tricky one. I put it on here on purpose. You're probably going to get this wrong. That's okay, all right? But the key thing is most of us will definitely or hopefully should know why Roman numeral 3 is correct, because that's what we've been practicing, where if your x equals 4 is a critical point, and when you evaluate all of your two endpoints and your critical point, if that one has the highest y value, then you know the absolute maximum is there on its interval. But there's one other reason why, or there's another one that would be okay here, and that's going to go back to 4, 4. I'm going to go to the, where is it? Not there. Is it in 4.3? It might be in 4.3. It is. Nope, I lied to you. Hold on. I'm going to find it. Maybe it's 4.6. No, it's got to be 4.7. Not 4.7, not 4.8. Where is it? Oh, no. Is it here? Nope. I'm going to pause and find it. Okay, I found it. It's in 4.5. So the second derivative test says that if your second derivative of your value for c, or your random value for x, is greater than or equal to 0, then your original function has a local minimum at letter c. All right, so that's what's happening in this one here. All right, I guess I should have said the other one. Where was that, 4.5? Nope. Yeah. So it's this one here, the second one once it clears up. We have a local maximum at x or at c because our second derivative of our value for c, in this case 4, is less than 0. So that just shows you that this one would also provide evidence that there's an absolute maximum at x equals 4 on this interval. So just be careful. A lot of us are going to pick 3 only, but the answer here is actually 2 and 3 because of that second derivative test. Okay, 32. Now 32 gives you the original function, and we're trying to figure out which of these answer choices could be the graph of the derivative. Okay? Now when you look at this, all right, the way that I always do this is I'm just trying to take, at any time, at any point, I'm trying to find the derivative using my slope of the tangent lines. So when I do this, I'm just mentally making, asking myself, where is the slope of this going to be, positive or negative? And so if you just, want to do it on your own, what I'm doing is I'm noticing that all of these are negative until you get here, where it's finally now the slope is 0, and now the slope of our tangent lines are positive until there, and then it's negative again forever, right? So that's how I kind of do it. So we're starting off where I should have negative values when I graph the derivative. So that's not starting off negative, right? That has starting off with positive values. So that one's going to be wrong for sure, all right? So when I look at these, if you also look at C is wrong, it never gets to be positive values, but we have positive values this whole time in between. From like here to here, the tangent lines are positive. So we should have positive y values in our graph, okay? Now, it looks like we're going to cross the x-axis twice because we have, let me kind of use a different color to show you. We have 2 times where the tangent line is 0. So I'm going to rule out D, because that crosses 3 times, all right? So really I'm down to E and B here for my possible choices, all right? And the reason I didn't choose E was because you'll notice that we're getting to another value where it would be 0, but we don't have 3 of them. We only have 2 of them. So really the only option here would be letter B. Let's go to 33. This is the same kind of problem, just going backwards. All right, they're giving you the derivative, and you've got to see which ones could possibly be the original, okay? It's the same kind of thing. In this case, I'm just looking at Roman numeral 1, 2, and 3 and going from there. So if I look at Roman numeral 1, it's saying that it's negative. The slope would be negative all the way until we finally get to 4. And then from 4, the slope is 0 the whole time. That's not happening here, right? In my derivative, we're starting out negative, but it does get positive, so that one's not going to work. If I do number 2, we're starting out negative, and then it turns to positive after 1. Okay, that makes sense. And we have, let me put some lines here to show you where we should cross the x-axis. So there and there. So we should have 3 times we cross. Boom, that's 3 times. I like it. All right, and then we have this right here is not continuous at 4, so that makes sense. This could work. Let's look at 3. Again, we've got 3 places where it's 0. Excuse me. And then it's actually not differentiable here, right? Remember that rough or, kind of sharp turn or sharp curve means it's not differentiable, which makes sense because when I look at the graph of the derivative, we don't have a value for 4. So 3 could also work. So the answer choice is going to be 2 or 3, which is E. Let's go to 34. Okay, so 34, same kind of thing. We've got f of x shown to us. Which of these could be the graph of the derivative? Now, if you'll notice, we have positive tangent lines until we hit this value up here where the tangent line is 0. And then we switch to negative tangent lines. And it looks like we could have possible values for 0 at the beginning and at the end. Okay? So I'm looking for really kind of three spots where we are touching or crossing the x-axis. This one only has 2. This one only has 2. This one only has 1. All right, so now it's down to A or C. The first thing I notice, if you look at my blue lines that I drew on the original, is those are positive. So I should start out with positive y values on my derivative. And what do you notice about C? C starts out with negative y values. So the only answer that makes sense is A. All right, let's move to a new section. 35. Now, 35 says, if this is the second derivative, what could be the original f of x function? So these next few questions are going to be about the lesson on antiderivatives or introducing you to basic integrals. Okay, so when I do this, right, if I'm trying to find, ultimately I'm trying to get to the original function, I need to kind of go backwards one step at a time. So they gave me the second derivative, so I'm going back to the first derivative. So watch what I write here. That's x squared, right? Because the derivative of x squared is 2x. And if I want the derivative to be cosine, I need to start out with the sine of x, right? Because the derivative of sine is cosine. But you notice it's a negative there, so I need this to be negative as well. That's not the answer, right? Because ultimately that's the first derivative, and I want the original function. So I got to back it up again. So 1/3 x cubed, right? Because 3 times 1/3 is 1, x squared. The derivative of cosine is is negative sine, so this is actually going to be plus. So I know my answer has to include this, all right? Now you'll notice that's not the answer, right? But it is up here in letter A. The reason they put minus x plus 1 is that when you take the first derivative, you'll end up getting minus 1. And then when you take the second derivative, that minus 1 will end up being nothing. All right, so that's why you really only needed in this question to figure out this first part in order to get this right. Okay, so 35 is A. Let's go to 36. Same type of problem. Let me rewrite this because it looks kind of wonky. This is the integral of x cubed minus 3x dx. All right, so to go backwards, we know it has to be x to the 4th power, but I want to make sure that's a 1 in front of x cubed, so I need to put 1/4 because 1/4 times 4 is 1. Same thing idea here. If I want to have 3 there, I need to write 3/2 because 3/2 times 2 would be 3. All right, and then you put a plus c because whatever constant you want to write there would be fine. So plus 6 minus 7 doesn't matter. It would be that. All right, and the only answer choice that has this is E. Let's do another integral, 37. All right, now I'm going to actually distribute all of this out first to get x to the 4th power plus 2x squared plus 1 dx. All right, so again, going backwards, I need to have x to the 5th power, but I want that to become 1x to the 4th power, so you got to throw 1/5 in front. Now I want this to be 2x squared, so I got to put a 3 here, and then when I multiply by that 3, all right, I need to get rid of a denominator of 3, so it's going to be 2/3. And then this one is just going to be x. The derivative of x is 1, and then plus your constant. So I'm looking for this as my answer choice, which looks like the last one, I believe. It does. 37 is E. 5 more to go. We're close. Now, 38 is a problem that we did almost identically to this problem. We did this in our optimization problems. I think we had an ellipse. We were trying to maximize the area of a rectangle in an ellipse. This is just half of that. It's a semicircle. So when you read all this stuff and it tells you that the derivative of the area changes from positive to negative, right? If you think about going from positive to negative, that's an absolute maximum. All right, so the moment that I read these answer choices that say minimum area, I know we're going to be wrong. So now it comes down to basically, did you read the directions or read the problem correctly? And it says that the width is 2 times x. So my dimensions are going to be 10 times the square root of 2, right, for that one of them. But my width, right, this is my length. My width is this times 2, so it's 20 times the square root of 2. All right, so that's why the answer is C for 38. Let's do 39. Again, I chose this one because we did a problem, the very first problem we did about optimizing the area of our garden with one of the sides being a wall. It wasn't a wall. Let me see. I can pull it up real fast. One of our sides was, maybe it was a wall. Yeah, a rock wall. This problem is essentially identical to this problem right here. Okay, so we're going to do the same kind of thing. Numbers will look different, but that's why I chose it. So we have our area. Remember, this is the wall, so it's just x, x, and y. So the area is x times y, but I don't want to differentiate yet because I have two unknown variables on the right-hand side, x and y. But we have the perimeter is 2x plus y, and that means we can only have 18 meters of fencing. So y is the same as 18 minus 2x. So I'm going to replace my y with 18 minus 2x. Distribute 18x minus 2x squared. So now I can differentiate. So take the derivative. You get 18 minus 4x. And to maximize this would be to set it equal to 0. So that's 18 equals 4x, or x equals 4.5. Okay, now it doesn't say, what are the dimensions? It says what's the maximum area. So I need to end up using this function here. And you can do two ways. You can find y if you want, or if you look at the one right below it, we actually have it with just x. So you can just plug into that one there. So the area is equal to 4.5 times 18 minus 2 times 4.5. So whatever that equals is going to be our answer. So use your calculator if you want. Go to Desmos. So we have 2 times 4.5. That's 9. So 9 times 4.5 is 40.5 meters squared. And the only one up here that's 40.5 meters squared is letter E. Let's go to 40. Now these last three, if I'm not mistaken, yep, these last three are all about L'Hopital's rule, which is a lesson that we just ended up doing recently. So in this one, it tells us that we have a function f, and then it gives us the g prime of x function, so the derivative of g. And it's known that the limit as x approaches infinity of g of x is equal to infinity. So in order to use L'Hopital's rule, I need to show that the limit as x approaches infinity of f of x is also infinity. If that's true, then I can use L'Hopital's rule, which is to take the derivative of each of these and put one on top and one on the bottom. So if I go to Desmos, I can show you this if you're having trouble with it. But I just pick like a big number for infinity. I'll just pick 1,000. So I'm really just looking at f of x first here. So 2 times 1,000 plus 3 times e to the negative 5 times 1,000. You'll notice, and the answer is just 2,000. That's because if I take this away, I take away the 2 times 1,000. And when you do e, or any base, to a, I'm going to say big negative number, which really is a small number, right? If I do e to the negative 5,000, let me actually erase it. There we go. Right, that's the same as 1 over e to the 5,000 power, right? And e to the 5,000 power is a very big number, all right? do 500, right? That's a huge number. So 1 over a huge number is a small number. And in this case, it approaches 0. So what I just proved is that the limit as x approaches infinity of this f of x function is also infinity. So that means I can find the derivative of this function f of x and then put it over the derivative of g of x, which they gave me, and see what I get. Okay? So the derivative of 2x is 2. Remember, our constant of 3, just leave it there. The derivative of the natural exponential function is you copy it down, and then you multiply by the derivative of what's in the exponent. In this case, the derivative of negative 5x, which is negative 5. So that's going to be 2 minus 15e to negative 5x power. All right, so that's going to go in my numerator. So the limit as x approaches infinity of 2 minus 15 times e to the negative 5x over 1 over x plus 4 times the cosine of 5 over x. Now watch what happens when you do this. All right, we just proved that if you raise e to a negative like 5,000, that's going to essentially be 0. So 2 minus 0 is going to be 2. And then in my denominator, I have 1 over x, which would be 1 over a really big number is a small number, which is essentially, let me write this down like this, which is essentially 0. All right, and then plus 5 over a really big number is going to be essentially 0. So the cosine of 0 is actually 1, and 4 times 1 is 4. So 2/4 reduces to 1/2, or b. Okay, last two. We have the limit as x approaches pi over 2. So the first thing I do is I plug in pi over 2. So 3 times the cosine pi over 2 over 2 times pi over 2 minus pi. All right, cosine of pi over 2, again, we've talked about this quadrantal before. That's going to be 0. 0 times 3 is 0. 2 times pi over 2 is pi. Pi minus pi is 0. So because I got 0 over 0, I can use L'Hopital's rule, which is to take the derivative of my top and bottom and try it again. So the derivative of 3 cosine x is actually negative 3 sine of x, right? Because the derivative of cosine is negative sine, over the derivative of 2x is 2, and the derivative of pi would be 0. So that's what it becomes. So now I'm going to plug in pi over 2 again, but this time into the derivatives. Okay, sine of pi over 2 is actually 1. So that's negative 3/2. So our answer here is A. Last one. I'm going to plug in 0. So if I plug in 0, I get e to the 0 power minus the cosine of 0 minus 2 times 0 all over 0 squared minus 2 times 0. Well, e to the 0 power, anything to the 0 power is 1. Cosine of 0 is 1, and that's 0 all over 0 minus 0, so that's 0 over 0. L'Hopital's rule exists here because we got 0 over 0, so let's take the derivative. Derivative of e to the power of x is e to the x times the derivative of x, which is just 1, so that's just copy it down. The derivative of cosine is negative sine, so that actually becomes positive sine of x, minus 2 all over 2x minus 2. So I'm doing the limit as x approaches 0 of this, so e to the 0 power plus the sine of 0 minus 2 all over 2 times 0 minus 2. Anything to the 0 power is 1. The sine of 0 is 0. So we get 1 minus 2, which is negative 1. 0 minus 2 is negative 2. That becomes a positive 1/2, or C. We did it, guys. That's it for part 2. Hopefully you can ask any questions in class, and good luck on the test.